Good morning. It's morning for me. I shouldn't say good morning for you because you don't know if it's morning or not. Too many things open. Oh, goodness. As I was working yesterday, where did my head go? I lost you. Well, it's still recording. You just may not see my face. Oh, I know what happened. There it is. Okay, I guess I need to keep that tab open. We are in our last lesson of algebra. Of algebra. Woohoo, we're done. No, we're our last lesson of Unit 4, Lesson 18. So our last lesson of the unit. We're tying everything together. So what we're doing today is use functions to model real-life situations and make predictions. Okay, that's our goal today. So to get started, look at our warm-up. Think about an electronic device with a battery that you have to charge on a regular basis. What device is it? Okay, I'm looking at my desk. I have my phone. I have my AirPods that are currently plugged in. I have the tablet I use to write with, and if you look, there's a blue light right there, which means that it's turned on and it does need a battery. I'm working on my computer, which is another thing that needs a battery that I have to charge on a regular basis. In fact, I should probably plug it in because if you look at the top of that screen share, my battery is not full. Okay. So, I've mentioned quite a few options. I said phone, AirPods, computer, etc. Sorry, I got a text on my charge device. So when you're using the device, about how long does it take the battery to go from 100% charged until the time you plug it in again and recharge? And we could say that depends. Okay, if my computer's not being used, then it can go for a few days. If I'm not on my phone a lot, if it's just there in case I need to talk to somebody, then quite a while. If I'm watching Netflix or FaceTiming with someone or, playing video games, which I don't do, on it, it'll lose its battery quite often, quite quickly. My AirPods, if I'm using them to actively listen to something for continuous time, then quite quickly. They charge so fast though. So when you're using the device, about how long does it take the battery to go from 100% charge until the time you plug it in again to recharge? It depends. About how long does it take to charge to 100% starting from zero or nearly zero? So my AirPods, I don't know, it's pretty fast. My phone, quite slower. I don't know how much time though, I've never timed it. My computer seems to be in between, somewhere in between fast and slow, medium speed. Suppose you plugged in your device when the battery is 50% charged. How long do you think it would take to recharge the device to 100% and compare it to the time the device was zero? Would it be exactly half the time, more than half the time, or less than half the time if we started from zero? And again, it depends. I'd assume if I start from 0% battery life and I'm trying to get to 100% battery life, it takes a set amount of time. If I'm at 50% battery life, it should take about half the time. Right? It should. If you just think about one device, okay? Again, those AirPods sort of surprised me in how fast they charge. Look, I just plugged them in this morning. No, not quite yet. All right. Moving on. Something I like about recording videos right now is I don't have to have a mask on. It makes me happy. I still don't put makeup on because the mask covers it, but now I'm just rambling on. Basically, I'm just reading. The summary here is times vary. Okay. All right. How long will it last? Okay. So a cell phone is plugged in to be charged. The table shows the percent of a battery power at some times after it was plugged in. At what time will the battery be 100% charged? Okay, no idea. All right, use the data to find out and explain or show your reasoning. All right, so we need a function here, right? We need a function. Okay, let's look. Sorry, I needed my handy dandy calculator. All right, so we are 10-minute, 20-minute increments. So if I look, here is 10 minutes. And we've gone from 9%. And here we are 20 minutes, or 10 minutes times 2. So we're 20 minutes, or 10 minutes and 10 minutes. So for 20 minutes, we're at 20%, or 10% and 10%. 10, 20, 30, and here we're another 10 minutes. And 8%. I'm going to average all of these. So 9 plus 10 plus 10 plus 8 divided by 4. We're about 9.25% every 10 minutes. All right, how much more percent do we need? We need 57 more percent to get to 100%. All right, if we're 9.25 every 10 minutes, I can take that 57% and divide by, like, how many times is that 9.25? Okay, I'm breaking it up into pieces. Okay, that 57% breaks into 9.25, groups of 9.25. There's six of them. Okay, so that means that 9.25% happens every 10 minutes, right? Let me do that different. So really we're at 9.25%, 9.25%, 9.25%, because remember that was 20 minutes, 9.25%, and then 9.25% times 6.16. So that is how many groups of 10 minutes there are. So really, that's going to be 60 minutes. We can say roughly 60 minutes or 1 hour. So 1 more hour. Or approximately 12:40 to 12:45. Because we have the 0.16. It's going to be fully charged. So it's linear is our assumption, and we just needed to figure out how much it increased per time. So it's 9.25% every 10 minutes. So we could do, honestly, we could have done like this too. 43 plus 9.25. Is 52.25, and that would be 10 minutes. and then plus 9.25 is 61.5, and that's another 10 minutes. Okay, we're not to full power yet. Plus 9.25 is 70.75, and that's another 10 minutes. So see, we could just repeat adding. It's the same as multiplication. Plus 9.25 is 80, and that's another 10 minutes. Sorry, I messed up how I was writing it. That should be a 2. Plus 9.25 is 89.25, and that's another 10 minutes. 10, 20, 30, 40, 50, plus 9.25 is 98.5. So that right there is 10, 20, 30, 40, 50, 60 minutes. And we are actually not quite there, so it should be a little bit more. And we could actually, if you want to take it a step further, we could find out what percentage of 16 is 60. So it should be, 60 minutes and 16 over 60, which is 60 minutes and 26 seconds. Okay, because 16 over 60 is 26. Okay, that was fun. Ooh, now we have a graph. Advanced battery usage. How long will it last? All right. Okay, what are we doing here? Let's read. This image shows the battery usage of a cell phone 9 hours since it was fully charged. It also shows a prediction that the battery would last 8 more hours. Okay, write an equation for a model that fits the data in the image and gives the percent of battery power P as a function of time since the phone was fully charged. Okay, show your reasoning. If you get stuck, consider creating a table of values or a scatter plot of the data. All right, there we are. I just needed the work in front of me. Okay, so we need an equation. All right, let's see if we can get that. Hold on. Okay, so I'm going to go back up here. It says here, consider creating a table of values. Right, that's what we're going to do, but we're going to come up here and work. Okay, so 9 hours ago. So really, we're gonna use this table. And we're going to do this at time, this being 0, and percent charged. What I want to say is our equation is going to be a linear equation. Knowing that m is our slope, which we have to calculate, and b is our y-intercept. What's cool is b is 100. That is where it is crossing the y-axis. So we really need to create a table of values so that we can calculate a slope or average rate of change. Okay, so we need to create a table of values so that we can calculate a slope, which is the same as our average rate of change. I'm going to find that in table of values. All right. Do you have any other information on this? Oh, no, so we're going to go here. So this would be 9 hours ago. So our time here would be 9. And our value, we can say that is about 52. So 9, 52. So a table will say that at time equals 0, we are 100% battery charged. And at time equals 9, we're about 52% battery charged. Okay? And that should be enough to find our slope. Sorry. It's not working. So I'm going to make sure I was leading you in the right direction. So our average rate of change is going to be change in y. So let's do 100 minus 52 over, so I just did 100 minus 52, so I need to do 0 minus 9. 100 minus 52, oh wait, calculator, there we are. 100 minus 52, divide by negative 9. So my average rate of change is negative 5.3, and that would be percent per hour. So my equation is going to be, now what units to bring this in? Power as a function of time. So power equals 100, y equals m. So that's not right. Negative 5.3. That would be t plus 100. Okay, mx plus b. So that is our function, right? And all I did was calculate my average rate of change, which I took this point and this point. So this would be 0, 100, and I calculated the slope. Now we're just assuming that it's linear, right? All right. So we did power equals negative 5.3 t plus 100. Based on your function, what percentage of power would the battery have 4 hours after this image was taken? So 4 hours after the image was taken, we would be, our graph, well, this would be 0, 9, 10, 11, 12, 13. We want to do 13, okay? So I can erase that. So we're doing time equals 13 for 4 hours. So P equals negative 5.3 times 13 plus 100. So on the calculator. So 31.1%. And I think we could all probably say that it really seems like at the end of our phone battery life, it dies really fast. At least mine. Let's see, 5 hours after image. So 5 hours would be t equals 14. I don't know if you guys feel the same way. So this would be P equals 5, negative 5.3 times 14 plus 100, 25.8. Okay, and that's my reasoning. Here are 2 more images that show the battery usage at 2 later times before the battery was charged again. How well does the function rope predict the battery power at 4 hours since the first image was taken? That is 13 and 14 hours after the battery was fully charged. Okay, so 13 hours ago, 29%, and we got 31%. I think that's pretty good. And then 14 hours ago, 7%. Nope, and we just talked about that. So we got 25.8. Okay, our model didn't predict it well at all. What do you notice about the change in the battery prediction between 13 and 14? It looks like between 13 and 14, our function looks like that, and then it just changes, right? So we've been studying piecewise functions. So this makes sense, where this is our model that we came up with, and this is a different model, right? Because it just plummeted at the end. Write a new equation for a function that would better fit the data in the last image. So we did 0 and 100%, and then we had 9 and 52%, and then 14 was 7%, right? Right there. And then let's just say, let's see, I don't know, 14.5 is 0%. So we need this function right here. We got one here. This one right here is p equals negative 5.3 t plus 100. All right, so we need that last one. So let's do our average rate of change. 7 minus 0 over 14 minus 14.5. So our slope is negative 14. So our function here would be p equals negative 14 t plus, and we have to figure out our y-intercept, which is still, well, if our slope has changed, our y-intercept has changed because our linear function would cross the y-axis way up here. So hold on a second, let me look something up. Yeah, I thought so. Let's do this a different way. Let me change colors to hope not confuse you. All right, so we really want the slope, but we're going to do the slope of this linear function. We're just not going to see the whole thing. All right, so we really want to do 100 minus 0 over 0 minus 14.5. So we are at negative 6.9 is our slope. So our function would be negative 6.9 t plus 100. Okay? So what we would do is write a function. Our power function equals negative 5.3 t plus 100 when our time is between 0 and 14. And then our function would be negative 6.9 t plus 100 when we are in between 14 and 14.5. So that is our piecewise function. And if we graphed it, it would go from 100 linear function until it hit 14, and then it would go straight down, 14.5. And this was about, what was it, 29%? Okay, piecewise function. All right, that's it for today. Good job in your last lesson.